Good morning. Good evening. From our experience, we know that people will keep coming, but we need to start. We have a big agenda. I am Valery Kuboevich, Executive Director of Mack Institute. It's our 13th launch of the Y Prize. The number is not kind of very lucky number, but we aren't superstitious, right? We have to stay positive as innovators. Thank you all for being here. Thank you for your interest. For us, what we do at Mack Institute, basically we take our faculty research and try to translate it into experiential learning for students and business practice. So Y Prize is probably one of our best initiatives in this sense. Really, it's about our engineering faculty's inventions and business faculty's knowledge how to bring those inventions into practice, how to commercialize them. So that's what you're going to do over the next few months. It goes fast, but fortunately it's not the only opportunity to work with these inventions. There are many subsequent steps you can take if you really get into that. So it's a journey rather than just one time kind of competition. We could have not done it on our own alone. Obviously, our inventors who are today here, Professor Mark Yim and Cynthia Sung, they contribute the projects we can work with, right, trying to commercialize. We have a big team here tonight from PCI, Penn Center for Innovation, who actually are looking at all inventions at Penn and are trying to identify the ones which are commercializable, accessible kind of for students, but not yet commercialized. So it's a difficult balance to find. The Venture Lab has been doing with us this, where's Sebastian, right here, for all these years, pretty much providing resources you can use to develop your projects. And then we have also our own team from Mack Institute, Terry, who has been running this competition for all these years. We have Kate, who is there kind of helping us to get organized and be here. And Valentina just joined our team, developing an innovation ecosystem around Penn, where Y Prize is part of our activities in this regard as well. Then what I'd like to say, what's different about tonight, we also asked PCI to give you some ideas, shape some expectations regarding dealing with licensed technologies. It presents its own challenges. We know that there are some barriers to overcome when you want to bring to the market licensed technology. And Terry Bray will present how some key points around this issue, and we are here to support you all the way through, right? If you're serious about it, at Mack Institute, we'll do whatever we can to overcome those challenges and barriers that might emerge. Beyond that, we have, as I said, very tight agenda, so I don't want to keep your time. A couple of suggestions just to you, to those teams that decide to proceed with these inventions. Stay in touch with us during the process. We have resources, we have time and interest in helping you making these things develop and make sure that your projects are strong when they're presented to the jury. Second, we offer a monetary prize, but it's not the only resource. Actually, the prize is supposed to be used for commercialization to launch your startup, right? But it's not the only resource we had for that purpose. There are many more resources we can provide in kind, so you can really achieve your goal. So always ask, always reach out, let us know what you need, and we'll see what we can help you with. Otherwise, good luck, and don't forget, after this introduction, we'll have reception and food where you can start forming your teams. And I hope to see you there and talk to you if there are any questions. Thank you for being here.
Bring up Professor Mark Yim, our first PI of the night. He's responsible for our snake robot arm technology.
Thanks. So this is going to, actually I call this CHAMPS, configurable, highly articulated, multi-purpose snake robot. There was a time when we were calling it a configurable, highly underactuated, multi-purpose snake robot, but that didn't really make a good acronym, so we don't use that one. So what is this? I don't know if you've seen this. Is the video from the Y Prize. Thanks. So we'll just go through this.
My name is Mark Yim. I'm a professor in mechanical engineering at UPenn. I'm also the director of the GRASP lab, which is the oldest robotics research lab in the country. The goal of the lab is to explore and push what's possible with robotics. So if you saw Spider-Man with Doc Ock, the guy with these long arms out of his back, that's essentially what we're trying to do. So we've been prototyping a set of modules. The current version has about 6 modules, and each module articulates like an elbow. The ultimate version, we're hoping will have something like 100. The problem is if you have a motor in each module, it starts to get really heavy. If you want it to be stronger, you have to put a bigger motor, but a bigger motor's heavier, and so they could barely hold their own weight. And that's where the real advancement comes in, how we're actually moving them. 1 or 2 motors drive this transmission down the whole arm, and each module can tap into that spinning transmission to get the power and the rotation as you need it. The interesting thing about this approach is that it can be rigid when it needs to, but it can also conform. If you have some structure and you want to wrap around it, the normal approach is you'd have to tell every degree of freedom how to move at the right angle exactly, which is very difficult to do, especially if you want to softly grab an object. This robot has the ability to apply the same forces around an object as it grabs it. It could be used for inspection, very tight spaces like engines or in a boat or an airplane or a car. The thing that I think is novel about this is that it can also apply forces. So we can reach into something and turn a bolt or grab an object or apply forces inside these constrained areas. We've been working with nurses. Moving patients around is something that they have to do all the time. Adjusting people in a bed or bringing them into a wheelchair. Anytime you have to transition, moving people around is hard and can often lead to injuries. So if we can have a robotic device that can help them move people around, that could be really useful. One of the things that I think is really exciting for me is that I am not sure what this robot could be really good for because it has all these different capabilities. One of the things that we need to do is find out what the right application could be and then focus on developing those particular capabilities. How far can we go in those capabilities are one of the directions that we are trying to figure out.
This is a breakthrough beyond your father's dreams.
Thank you. Silly. So then I think I was pretty impressed with the video editor guy who put this together. Partially because he just got so many different pieces to come together. All these other things. Okay, so there have been other robot arms like this in the sense of, highly articulated, especially for things like...
The Optimus robot is Tesla's boldest gamble.
Especially for things like inspection. So there are 2 primary differences between this work and the existing work. One is that it can actually be expected to be much cheaper, much lower cost. Okay, so these are examples of things from decades ago, snake-like robots. And usually the snake-like robots are always moving on the ground because they aren't strong enough to lift them up. If you were to cantilever them out, usually you can only hold maybe 4, 5, 6 modules before it just can't hold itself up. There are these soft robots that are similar. That's a new thing from the past decade, roughly, where people are talking about making elephant arms or things out of rubber and pneumatics and that type of thing. Those are really weak. Almost always when you have a manipulator, they always show it hanging down, and they do things below it because it can't even do it. It can't even lift itself up just because it's relatively weak. So this is the type of thing that currently exists, which is cable-driven. There is a company currently that's now a subsidiary of GE, where they have this 24-link arm, 24 degrees of freedom, And it does things inspection inside of airplane engines and airplane wings and that type of thing. This whole structure back here is part of the robot. So they have cables running down here, and all of the motors are behind it. And all the ones that are like this type of cable-driven system have this giant structure behind it with one motor for every degree of freedom. That's why they're capable of doing things, but they can't really have much of a payload at the end. Because things the weight just kind of adds up. And also it's what makes it really expensive. So I think we can probably get maybe an order of magnitude lower cost. With the primary thing that we're doing is the transmission that we have. This is I'm planning for this to have roughly, we can have it scalable. We can have up to 100 degrees of freedom, maybe more. Things start to get more difficult as you add more and more degrees, more and more articulations. The main thing is the strength to weight ratio. The way we have the transmission, you don't have to have a motor at every part. You just have a small, if you saw in the video, there's a little solenoid which can be very small and weak. And we have a transmission which you have just a couple motors at the base, which pass the power down, the mechanical power down, and the little solenoids or other types of clutches that are very lightweight that can engage in that transmission in order to get the turn you like. So I estimate it'll be about $3,000 is what I think it'll be for about 100 articulation robot arm. Currently, they're probably somewhere between $50,000 and $100,000 for something that has 24 degrees of freedom, the commercially available ones. The other unique thing is that besides the typical thing that you use with an inspection arm is what they call follow the leader, where you have the robot, the body of the robot follows the head, and so you can snake inside wherever you need to go to, whatever the path may be. So this robot can do that, but it also has several other modalities which make it kind of interesting. And part of it comes from having so many degrees of freedom. Okay. So this is just a little bit more details. If anyone's curious about the details about how this works, one of the key things that's kind of interesting is it's gear driven. It's a gear transmission, and it's not cable driven, which most of the other snake systems are. We figured out how the transmission works. All the equations for where things go as you go down the line. I won't go into details. The reachable space is interesting because there's 100 degrees of freedom. The space is a 100-dimensional space, which means that you can reach anywhere. You have all these different type of combinations of things you can do. So one of the things we can do is you can simulate like another serial robot arm we might typically have robot arms that are defined by the link lengths. How long is this part of your arm, and then the next part of your arm, and then the degrees of freedom at the ends. This system can emulate other robot, essentially almost any robot that has these revolute joints at each end. It can't do everything in the sense that one of the things that we're losing by having this type of transmission is we only have one or two motors instead of 6 motors or 100 motors, which means that there's this thing we call a constant speed constraint. The arms can move, but every joint has to move at the same speed. Whereas if you had 100 degrees of freedom, every arm can move however you like. And the thing is, you have to switch between the motors. The transmission has to switch. And so if you have some kind of complex motion, you might have to do a lot of switches, which is theoretically possible, but the motion tends to be a little bit more, not as smooth. We can do the follow leader. The other interesting thing is we can do this when you have so much different ways of doing things. Like the worst way to lift up if you're a weightlifter or something, or if you're a weightlifter, you might do this on purpose. But the worst way to lift something is like straight out, in terms of you have this weight here, you have all this torque in the shoulder joint. In order to do something to carry a heavier weight, instead of just going straight out, you might bring it out this way and then go up. so you don't have all that torque with this long radial arm. And because this has so many degrees of freedom, you can take advantage of these this kind of minimizing the amount of the radial arm that you have to minimize. You can minimize the torque, and you can also do these things where you take advantage of the singularities that you have in the Jacobian space. You can actually get near infinite mechanical advantage. So there's ways to apply very large load, carry very large load because you have the ability to configure in different orientations. We also have the ability to conform to things. So even without sensing and knowing what angles you need, you could have some joints which are free to move somewhat. And so as you move, if the arm bumps into something, it'll naturally curl around it without having to tell it to move this degree of freedom. Just as you move and you make contact, it'll naturally curl around something. And ultimately, when you have surrounding the object, you'll end up with an equal force on each contact point, which will minimize the maximum stress that you might have on the object that you're grabbing. There are some limitations and currently that we're exploring, which is taking advantage of this mechanical advantage means that you also rely on the structural strength of the system. So you have to design the system so it's actually the strength ratio of the structure has to be different. So you might need to have something like metal pieces close up and then plastic as you go out in order to maximize the strength to weight ratio, which we're still exploring. Backlash is currently a huge problem. The way that, because the modules build up end to end, the backlash adds as you add more and more. We actually have a new transmission that we're currently prototyping that I'm talking to PCI about filing an update to the patent for this new version, which will have better backlash problems. Friction is also a big problem, which I think will also be solved with this new transmission, but I won't go into details on that. So I'm going to stop the presentation here and maybe just leave room for questions. Maybe that's the best way. I've got a train to catch, so I'm not going to be able to stay after, or I'm going to miss Professor Sung's. I already know what it is, but it's really cool stuff. But it's not that I'm not interested in. But I do need to. So maybe you can leave the last. How much time do I have? Another.
We have about 10 minutes.
10 minutes for questions. Be more interactive. Yeah.
So you mentioned that you're currently working with nurses at hospitals to help them move patients around. So how do you envision incorporating that into the hospital? Like, are you putting the arm into the chairs and things? Or?
Yeah, exactly. It would be mounted into the infrastructure, ideally. So one of the things they have currently in the hospital is something called a Hoyer lift, which is this big frame that you bring up to the patient and you wrap it around them and pull them up, and that way that's how you can move them from bed to chair or chair to toilet or that kind of thing. So they already have some kind of infrastructure for that, and we might be able to do something similar. Yeah.
So for the quoted base cost of $3,000 for the 100 articulation arm, like say we have an application that doesn't require 100 articulations. Do you have any idea of how the cost would scale with each articulation?
Yeah, so the base cost is probably going to be around $2,000, and then the added cost is much less than per model.
There's another question on that side.
So you mentioned strength also being an issue, and I'm assuming that human bodies would probably weigh quite a couple of pounds. And so, do you envision them having interchangeable pieces? Then this could be applied, for example, in a kitchen or in a hospital.
Yeah, so that's one of the interesting things. Well, one of the things that we haven't settled on is the scale, like exactly how. Currently, the models are about this wide in diameter, and so we're looking at something that may be 10 meters long, but it can be made smaller. It starts to get difficult to make it really small, but for doing something in the kitchen, you might want something smaller. I don't think you can swap out.
I'm envisioning some have already come out like burger flippers, right? They're like there are these robots. So I'm envisioning like a robot like this could eventually, I guess, do more than just flip my burger on the line, is what I'm thinking. Like, could it saute a pig and flip an omelet? You know, I'm thinking on.
Yeah. Okay. So this is really important. So the current way of doing a lot of the kitchen stuff, they use an industrial robot arm, which is super precise. This arm is likely to not be as precise. And so if you don't need too much precision, it probably works pretty well at much lower cost.
Okay. Oh, absolutely.
But also, different ways.
So I just want to ask, like, how does the robot actually grasp onto things? Is it like a hand at the end, or is it just wrapping around them?
Okay, so that's another thing we're currently working on, which there are a lot of options. We can do, end effectors like Babcock or whatever. But the more interesting thing is that if you have a large object, it can wrap around it. Theoretically, if it's close or for long enough, you could wrap 2 or 3 times around the object and grab it that way.
How does the arm work in terms of replacing motors and gears? Is it easy to do, or does it render the entire arm useless?
So it should be relatively easy to. It should be relatively easy to add modules on and replace things that way. The way I currently have it designed is kind of a pain. Because you have to, you add things one at a time at the end. If you want to change this one, you got to deconstruct it from the end down, which is basically the worst way to do it. But in future versions, it should be. It's basically modular. You should be able to just swap out a bad module and put it in there.
Are there any trade-offs of scaling it down to like smaller sizes?
Trade-offs. So the funny thing is, going smaller doesn't necessarily make it cheaper, just because the way we pass it through each element. So you don't. There may remain roughly the same per module. The cost per module may be the same at mostly until you get really large. But between an inch and 5 or 10 inches, it may be roughly the same per module.
What are some of the material constraints that you've seen so far with jams?
So the current structure, which is all 3D printed, it probably wouldn't be able to support 100 modules with a 100-pound weight at the end. It would definitely break with 100 pounds weight. It might even break with much less than that with the 3D printed structures at the base. So what we may need to do is have metal structures at the beginning, and it's usually structural failures, buckling, or the stresses that you've already calculated.
Hi. Has CHIMPS currently been tested for how much force it can apply?
I've done some of the theoretical analysis of what I think it can do, and they're all just almost back of the envelope. So they could be off by order of magnitude. So I think it can do. We're designing it to be 100 modules, 10 meters, and I think it's maybe between 10 and 100 pounds at the end is the goal. Yeah.
On the manufacturing, how long does it take to manufacture one? How expensive is the manufacturing equipment? And I think those would be.
Okay, so the current prototype we're looking at is all 3D printed. So it just takes however long it takes to 3D print these structures. They're not optimal. They're not as strong as they need to be. We're not going to get the 10 meter length. But for 5, 10, 20 modules, 3D printed structures should work with low masses. So that's not really scaled up manufacturing. This is all prototyping. If we were to go to some more mass production techniques, this just scales up using standard. There's nothing special with the structures.
So you mentioned the modules should be interchangeable after you get the final product. For the degrees of freedom, would those also be interchangeable? Like, would you be able to adjust something from 100 to 80 and take those 20 and move it to another arm?
Yeah. So theoretically, kinematically, all the modules are exactly the same. If we have some of the stronger ones, the plastic ones, then they aren't necessarily. You don't want the metal ones at the end of an arm, but otherwise, theoretically, they're all the
Do you have an idea of what the lift ratio is going to be when you are able to manufacture it with the kind of the materials you prefer? Or what the goal is? Like, most of them can't even lift their own weight, is what you were saying. And so, are you trying to lift 10 times its weight, 100 times its weight? What's your goal?
Okay, so there's a thing we call characteristic strength, which is basically how many modules on an end can you hold yourself with just your own weight at all.
Okay.
No cable.
Yeah.
And that, with the motors on each module, is usually 6.
Okay.
People haven't gotten more than 6 or maybe 10. Well,
okay, so that is the goal. Okay.
That's the gotcha.
How did you determine 100 as a goal for the number of articulations you wanted? Was it like a specific application, or was that the limit of the technology?
So, yeah, I'm just looking at the limit. Currently, in all the literature that we've seen, 24 is like the most. There is one other system that has 100 articulations, but it can only do something very simple. But we're trying to make something a little bit more arbitrary. It could theoretically be 1,000. That would be the interesting science that we're looking at.
One more, Mark? Yeah.
How energy intensive is like how does it use a lot of electricity?
It could theoretically. The nice thing is that it has a lot of variability because it has so many articulations, and so theoretically we could do things which are aimed towards energy efficiency, but we haven't yet. Real quick.
Yeah, would adding more length or articulations to the arm affect the number of motors at the base?
No, which is the interesting thing. You just have 1 or 2 motors, and you add as many as you like, with these little things that engage the main transmission.
When there's a failure, where's the failure? Where do some typical failures come?
Yeah, so that's the thing that we need to research. And there's all kinds of places where failures could occur, but we don't know yet until we actually build it. But yeah, there's a million places that failures could be. And that's going to be the ultimate thing that we have to figure out.
Thank you, Professor Yam. I'm going to bring up Professor Sung in 1 second, but and I'll mention more about this at the end of the night. We have a lot to cover tonight. Next week, we're going to host another event that will take a deeper dive into the technology. So stay tuned for that information. It's going to be on, I believe it's October 1st, hopefully over at the engineering school with members of the professors' labs to be able to spend some more time on the technology itself. So if you get your questions answered tonight, you'll be able to have that opportunity next week. So thanks again to Professor Yim. One more thing about him. 13 years ago when we started this competition, it was Professor Yim and Dean Vijay Kumar and David Shu, who I don't think is here. So we can thank Professor Yim for this. He's still sticking around helping us out 13 years later. So thank you very much. Okay, so now we're going to bring up Professor Cynthia Sung to talk about her reprogrammable matter by folding technology. Yeah, I want to play the video, and then you can pick up, and then I'll play this while you're doing it. Okay, we're going to start by playing her video.
I'm Cynthia Sung. I'm an assistant professor in mechanical engineering at Penn and a member of the GRASP lab, that's the General Robotics Automation Sensing and Perception lab. The project that we've been working on is about taking advantage of origami-inspired design in order to create transformable shapes.
A lot of my work focuses on programmable matter and self-folding origami structures. So how can you give these origami shapes the ability to shape change to do some sort of task?
We can combine hinges or folds for an origami structure with magnetic actuation to take 2D magnetic sheets and then automatically fold them into complex 3D structures.
There's two major steps. So the first is the actual fabrication of the sheet, which has 3 different layers, where the top and the bottom layer are made of this magnetic material, and then the middle layer is this connective mesh material, and it's to hold all of the faces together. The second step is to take that sheet and put it onto the conveyor belt, and then you tell the entire system that you want it to fold into, say, an airplane or a boat. And then you kind of just click go. It brings the sheet over to our programming head to program the individual magnetic panels with a particular magnetic polarity. Then it's going to bring that sheet to a particular folding coil set. And then the system will automatically start this actuation or folding sequence, depending on what the finalized structure is. The folding occurs in less than 1 second.
One of the big advantages of this system is that we're able to really easily execute multi-step folding sequences. We can rewrite the program even in the folded state and then continue to fold the structure over multiple steps. So now you can get a recyclable sheet, which you can fold into one shape, unfold, fold into a different shape, and basically customize to use as you need. There's a lot of interest in creating these kind of transformers, right? There's tables that open and close in order to get bigger or smaller. There are stools that turn into ladders. You can change a sitting desk into a standing desk. What we're trying to do with the system is that idea, but on a more extreme scale.
What excites me the most is having people come up with ideas about how to use the system. Every time I meet origami artists or engineers, they're all like, what are you going to fold next? And I was like, well, what do you want me to fold next? I know the technology really well, but I'm not quite sure what to use it for.
Maybe in the future we can think about sheets of magnetic material that can change into a toolbox of tools. You can change into a screwdriver if you need to screw, or a wrench if you need to tighten a nut, or change into a hammer if you need to hit something. We don't yet see that capability currently in the real world because people don't really know how to design or fabricate those sorts of structures. And with this system, we're really trying to push the fabrication for those sorts of things.
Great. So thank you everybody for coming today. I'm Cynthia Sung. Gabriel Unger, who was the student you saw in this video, is also here joining us today. We're really excited to share our technology with you and find out what cool ideas you have for applying this platform. So just to give you all a little bit of background, our lab's expertise is in origami engineering, and we're interested in how we can take advantage of folded structures in different areas, particularly for us in robotics. What you're seeing here are some examples of different places where people have folded things that you may see in your everyday lives. So this here is a company that decided to create foldable furniture. So those of you who are in your dorms right now can get some cardboard and can fold it into a chair that can actually hold your own weight. And when you move out of your dorm, you put it in the recycle bin. You don't need to carry this furniture around with you forever. This isn't the only example right here. Up top, we have a tower in Abu Dhabi where they're using these folded structures to create shades, right? So now you get some nice aesthetics in addition to functionality, where they can control how much light is going into the rooms in these buildings. You can find biomedical applications where folding is used to deploy and expand structures, in this case it's an extent, or in space, right, where this is an example of a telescope lens that was folded into a small size to send it up into space and then deployed outside. So we're interested in seeing whether these sorts of ability to fold, reconfigure, get really interesting 3D shapes from 2D sheets can be extended to other application areas. But one of the challenges with these sorts of structures is that most of them have to be assembled manually, so you have to really love folding to put them together, right? And so one of the things we've been doing is trying to explore how we can create structures that fold themselves. This is an old video from 2015 where we tried to do this, and actually this is also very similar to what a lot of other groups do around the world, where we embedded active materials into a folded structure. When you expose this structure to heat, for example, it'll fold itself into, in this case, this little crawly robot. And then now you have this 3D shape that assembled itself within a couple of seconds, and you don't necessarily need to be an origami enthusiast to build this robot yourself, right? So these sorts of things have existed, and people know how to build these self-folding structures, but the challenge is if you look at this video, this whole structure folds itself, but then it can't unfold, you can't change its shape. The shape of this structure is embedded directly into the fold pattern, so we can only fold into this one shape, right? And so what we were interested in was, well, what happens if we want to create more complex structures? What if we want structures that we can reprogram and refold and kind of do this process repeatedly? So this is the system that you saw in the video just now. Actually, the edited video did a really good job of talking about the different components, so I'm not going to really go through all of them, except to say that the main components that we're really excited in here is this magnetic sheet, which paired with this magnetic right head allows us to basically program the folding behavior of this material at a pixel level. So what you're seeing here is a picture of the sheet. It's just black. It's like refrigerator magnet. So you take that, you put in the laser cutter, you can cut out the fold pattern. But then if you take a magnetic right hand electromagnet and you go in and you put that magnet really close to the sheet at particular places, you can program that sheet with north and south facing fields. This is basically exactly the same way your hard drive stores data. Right? So your hard drive is also storing data magnetically. That's what we're doing on these sheets. Now, what's interesting is that when the sheet then gets exposed to an external magnetic field, it'll self-fold, right? So you saw videos earlier of examples of the sorts of things that can be folded using these structures. I'm just going to have this video play in the background. But it's really an automated process now that we've developed for allowing us to program and then fold these structures, and then you can reprogram them and refold them as you need. What we think is really exciting about this is that, well, in this case, you're seeing a very specific magnetic laminate that we're programming. It's basically this refrigerator magnet, a polyester mesh, and then a refrigerator magnet on the third layer. And that allows us to get this, this particular pattern. But actually, the fabrication process for creating these sorts of structures, we think, is quite general. So what we've developed is this laminate-based fabrication approach where you take these layers of passive material, magnetic material, potentially active material, and sometimes even circuitry, and you can put them in layers to create these multi-material sheets. As long as you can make sure the sheets adhere together, then each of the layers provides your structure with some kind of functionality. So in this case, our magnetic layers are giving us the ability to do this self-folding. But you see in this diagram, we can also add in smart materials for response to heat. You can put in circuitry there to add electronic components, right? And depending on what you want this structure to do, you can change the materials in this structure. So, for example, one of the things that we've done most recently is we've also embedded, We've also embedded, for example, PLA that you might get out of your 3D printer. Right, so you can layer these magnetic sheets together with PLA layers, and now you have a layer that's both thermally responsive but also potentially stiff. And so you can think of the structures that take advantage of the magnetic component to fold. You can heat the structure in order to soften the middle layer, fold it into place, and then when you pull down the structure, you get more solid, folded 3D structures that can now bear load. So this structure here is about 2 grams, but it's carrying this 1 kilogram mass after it's folded, super lightweight, but is able to achieve this shape. Not only that, but one of the things that we've seen is that the resolution at which we can program these structures is really, really controllable. So because we're dealing with electromagnetics, as long as we can as long as we can create a large enough electromagnetic field, we can overwrite whatever existing magnetic program is on the sheet. Which means that regardless of the size of your magnetic right head, you can overwrite what you've already written to get smaller and smaller pieces, which means you can change the resolution of your magnetic program. Right, so what you're seeing here are different resolutions of checkerboards that we programmed to demonstrate this ability to change resolution. And now, not only that, but we can support this sort of programming with a graphical user interface where we can directly convert things that you might want to program, in this case, north and south facing fields on particular faces, into a magnetic program at a particular resolution and automatically send it to the system for fabrication. So we've folded a whole bunch of different structures using this system. You're seeing examples up top. And also one video in the middle. A lot of these are just origami patterns that we found in a book that were things that we liked. None of them really have any, specific intended functionality, but you can see the range of different types of shapes that we can create. we've also taken the exact same shapes, unfolded them, reprogrammed them. And what you're seeing in this plot here is the change in magnetic field over multiple programming cycles. And what you should be seeing is that there's no change in magnitude of magnetic field over multiple programming cycles, right? And so basically, what we found is that this sheet is really reprogrammable, and so you get a lot of repeatability and consistency over these different programming modes, which means that you can take the exact same sheet, reprogram it, and change it into these different shapes. So this here is an example of what is known as a universal fold pattern. It's provably able to produce any 3D structure to within the resolution of 1 square of this pattern. And so you can take this pattern, if you put the right program on it, you can pretty much achieve anything that you want up to the resolution constraint, of course. Our use of magnetic fields also gives us pretty good control over fold angles. And so what you're seeing here is a plot of the input magnetic field signal compared to the output fold angle. I'm not going to get into the details here, but Gabe can talk more about it when we actually have the technical details night. We can also then, as I said before, integrate electronics. So what you're seeing here is an example where we folded a structure now with circuitry on it. You can fold it into a P, have LEDs, and have these sorts of active structures. In this case, we call it our foldable display. But you can kind of imagine the sorts of things you might be able to embed, not just LEDs, but maybe sensors or actuators. Sort of. And the final thing I'll land on is, in the video, we mentioned potentially thinking about future reconfigurable tooling. This is the direction that we've started to move in, actually in the last 2 weeks. So what you're seeing here is a video where, here we have different size screws, and inside of this coil, we have this magnetically reconfigurable structure that can change its shape to adjust to these different screw sizes. What I really like about this video is that it uses the exact same technology that I've been showing you for the whole presentation, but rather than having everything in one long conveyor belt and everything on a desk, actually everything, the coil, the heating element, the pattern that is reconfiguring, is all embedded inside of this one object, which means that now you can think about portable versions of the system that you can put on a robot arm or some other thing to get reconfiguration on the fly. So that was a very quick overview of our system, and I'm also happy to answer any questions.
Are the checkerboard patterns for the magnetic polarity, are those human created, or is there some sort of algorithm that spits those out?
Yeah, so in our case, the checkerboard pattern was human created, although you can also create it automatically, right? Basically, once you set the pixel size for your system, you're just alternating the south-facing pixels, and so the system can go in and program that automatically. Yes?
It seems like there's, you're able to program these pixels to be really small. Are there any limitations to the size that you can make the magnetic strip with the mesh in it?
Yes, so in our case, we're using off-the-shelf components. So we bought all of our magnetic sheets off Amazon, and then also fabricated them all in the Veeam RPL lab. And so we have practical limitations in resolution just due to the kinds of materials and laser cutters we've been using. If you were able to use a higher resolution cutter, or you had a thinner sheet or something, then you would be able to scale the system down. We have not explored that too much yet, but we should be able to.
Thank you.
Yep.
What's the scalability of the origami pieces if the magnetic force is no longer strong enough to actually fold?
Sorry, what's the beginning?
The scalability of the magnetic pieces until they can't fold anymore?
Yes. So the scalability of the origami structures, it really depends on the magnitude of the magnetic fields that you can produce. In our case, our programming fields are something about 300 millitesla, and then our folding fields are around 25. But these are kind of within the practical limitations of desktop coils that we can produce in the lab. Practically, I guess the largest magnetic coil that I can think of we can realize is an MRI machine that creates an order of 1 or 2 Teslas. right? And so there are large ranges of magnetic fields that you can generate, and the force that you can produce to fold the structure will scale linearly with the magnetic field. The thing that you need to combat is gravity and friction, right? And so your mass is going to scale cubically with the dimension of your structure, and so you can balance those forces. Yep.
Are there any fatigue limits to reprogramming the medium? Let's say you have it in one polarity, and then for another application you decide you want to have it in another polarity, or the mesh itself is different. So what are the fatigue limits for that case?
Yes, so yes, as you've identified, the fatigue that is going to show up in the system is mostly in the edges, right, because we're taking advantage of folding. In our case, for really thin meshes, we haven't seen really any fatigue over thousands of cycles of programming. For thicker materials, if you're using like some kind of like plastic that's maybe 1 or 2 mil, you might see fatigue after a dozen cycles. But it really depends on the particular material and thickness of material you're using, as well as the folding that you're trying to use.
I'm sorry, the question wasn't there. I was asking about the magnets themselves. You're going to reprogram them for different applications.
Yes, we haven't seen any change in magnetic strength over hundreds of programs.
Take one more.
Is there anything special about the refrigerator magnet material? It's just that it's cheap and available?
It's just very cheap and available. So we got some of that. There's also like the magnets that come in rolls for like making bumper stickers on your car. Those are also cheap and readily available. I will say that those sorts of magnets are usually lower in strength than like the rare earth magnets or really, really strong ones you might see in research labs or like really high-end applications. And so if you wanted higher forces, you wouldn't go for refrigerator magnets. But in our case, we did because it was cheap.
Thank you.
Okay, thank you.
Okay, now we're going to bring up Sebastian Jeremio. Did I say that?
That's all right.
All right. To talk about the resources available to our Wi-Fi participants at the Venture Lab.
Thank you so much. Good evening, everybody. How many of you have been to Tangen Hall or been in the Venture Lab? Show of hands. A number of you, but still some that haven't. So my name is Sebastian Jaramillo. Thank you for trying. I really appreciate it. You can all call me Sebastian. It's fine. I am the Director of Operations and Community over at Venture Lab. I run the physical building itself and also help grow its community, so I oversee the student board and all the events that happen at Tangen Hall. Our mission is to empower students to found, scale, innovate, and grow their businesses. Businesses that we hope will be enduring ones that solve the world's problems, large and small. Probably says that much better back there, but that's the gist of it. We have a lot of resources. I think Valerie said it best. We are here to help you guys build. We have physical resources in our labs, but we also have financial resources and program co-curricular resources to help you develop your concept, build MVPs, whether they be physical or digital. So we have things, all these programs are available to you. I think the ones that are most interesting are the VIP program, the Startup Challenge, and the Innovation Fund. They're ones that provide funds for you to be able to, for the Innovation Fund, for example, get your MVP or initial concept off the ground. VIP is the Venture Initiation Program. It has two states, the Incubator and Accelerator. You apply to both of the two. You apply and you can figure out where you end up in that process, but that is one that will help guide you through the development of your venture. We have a variety of things, community events, a venture development course that helps you kind of self-guided course to go through, coaching sessions, visiting experts, really a plethora of resources for you to be able to kind of ask questions in the areas that you don't know, or just dig in and tinker, as I like to say. So we have food lab, retail lab, digital design studio, fabrication studios. The fabrication studios go deep, so we have a mechatronics lab, we have 3D printers, laser etchers. We just got a ceramic 3D printer, or it's printing in another material that is not plastic. And so check with Taylor Computer. I just saw it today for the first time. So there are a lot of resources there. We are 7 different floors, 8 different labs, about 86,000 square feet of entrepreneurial prowess. It's one of the largest spaces of entrepreneurship in the university. We offer everything free. We take no equity for none of the awards that we give. And so really it's a unique space for entrepreneurs in that sense. We offer 50 free 3D prints a semester. And as long as you're not doing, decorations for your room, really you can probably push that limit. So I say to everybody, join Venture Lab, get membership. We accept everybody. We just like to know who's in the building because we're off campus. And so I'm the person that gives you access. If you have any issues with getting access to the building, please let me know. We're open 7 days a week, 7 a.m. to 2 a.m. for those members. If not, it's only open Monday to Friday, 7 a.m. to 9 p.m. And so it's a great resource, even if it's just to study. I also like to say it's like a Hadron Collider of ideas. If you're not there, you're not going to spark something and find your co-founder or spark that next great idea. So our studios, team reservations happen through there, and you get access to the newsletter. That's going to tell you when our applications go out for the different awards, for the different programs, and really a great way to stay in touch with us and know when our events are happening, when the visiting experts are coming aboard. All right, VIP. You'll hear VIP, VIPC, VIPX, all this stuff. It is an incubator and accelerator program. We award up to $10,000 to the teams that are accepted into VIPX. We now have dedicated space in the building, so you have dedicated desks for you and your team to work on the 3rd floor. And then a bunch of advisors, entrepreneurs in residence, and alumni mentors that we help bring to the building to help guide you. QUIF is also another program that you guys can use. It's the Innovation Fund. They award between $500 and $5,000, both for your initial concept phase or for your kind of MVP creation. We have 2 applications, 2 in the spring and 2 in the fall, and they are actually students that make these decisions. And so if you want to get onto the QUIF team, you can also apply for that. Normally that starts in the beginning of the year. We gave out over 145 awards last year, totaling over $200,000. And so really of non-dilutive funds, we take 0 equity. That is very important. All right, the Startup Challenge is another way for you guys to win funds. Applications will probably open up in November. About 100 teams normally apply. We boil that down to semifinals and then finals with 8 teams. Grand prize is $50,000, and then there's a bunch of 20s and 10s hanging out in there. Specifically one around the innovation and social impact, and there's a bunch of different awards there, as well as a award of the People's Choice Award. So bring your friends. All right, and this is one example of a business that is incredibly successfully ocular implant that helps prevent the progression of glaucoma using one of the materials from engineering. And so I'm sure that you guys know about it a little bit better than I am. Actually, it came before my time, but they did win the Penn's Y Prize and have raised over $10 million. So that is Venture Lab, our resources, but I'm here to answer any questions. I'm an open book, undergrad from 2010, and happy to guide you guys through the path of entrepreneurship because I did not get the same type of support when I was here. They were just nascent and young in the Y Prize, and we did not really exist as Venture Lab. And so I'm happy to answer any questions if you have.
Yes, Sebastian, could you say a few words about during this period as the teams work on the project? My understanding was there's resources available for self-guided kind of learning, plus VIP materials might be relevant, right? So how can they access those without enrolling into a specific program?
So that is through the membership. You guys will get access to the Canvas, which has all of those materials, including the self-guided development course that I mentioned on there as one of the resources. So just sign up for membership. That is the way to get access to all that information. It will live on the Canvas. That's how you also apply for the training session for our 3D printing labs, fabrication studios, CNC machines. Now we have a kiln that can do pottery. And so there's a whole bunch of resources.
And what we know from our experience, usually teams use this time within Y Prize to develop the first iteration of their proposals. Then you can go in the spring into the Startup Challenge and then have another iteration, right? Because these are challenging, high-tech projects, require a few iterations. That's the best way maybe to proceed.
Thank you, and if you have questions, I will hang out.
Thanks so much. Let me get him set up here. I want to bring up Mr. Terry Bray from PCI. He's the Executive Director of Licensing of the Physical Sciences and Engineering. Just give me 1 second here, and I'll get you queued up.
Okay, thank you, Terry.
You're welcome.
Good evening, everyone. Thanks for coming out tonight. So I just want to talk a little bit about PCI, Penn Center for Innovation, sort of how participants in the Y Prize competition, and particularly the winners, might interact with us. Also sort of where we fit in the innovation ecosystem, both within Penn as well as sort of the greater Philadelphia area, other partners we work with, other resources that might be available, just to give you a sense of sort of how we might be able to help you as you go through this Y Prize process. So we've been very happy to support the Y Prize for a number of years. We put forth the inventors and technologies that are available for you to pick from to actually try to build a business case around. We provide the IP, and you may engage with us in one of several different ways. So the winners of the Y Prize will have the opportunity to engage with us to actually get commercial rights through a legal agreement, either an option or a license agreement typically. And I can talk a little bit more about what those are, but they're going to have both financial and performance terms in terms of how you're going to move the technology forward. The terms of these agreements are going to be negotiated consistent with Penn policies. They'll include financial and diligence terms, as I noted. We can also provide educational opportunities for you, point you to resources both within Penn but also external to Penn that might be helpful for you in your journey in trying to develop a commercial case for these different technologies. Just want to talk a little bit about where we fit in the ecosystem within Penn. So we touch a number of different organizations. We do a lot of things with programs and entrepreneurial education. We manage all the results of the research portfolio that might be considered intellectual property. We work with the Penn Innovation Center, which is a physical incubation space where companies can take space to actually get their companies launched and to gain traction. And we also work with a lot of accelerators and startup service providers. We work with a lot of different technologies on campus. It's a very diverse range of research that goes on campus. These are some of the different technology areas that we work with. We have various other programs and associations that we work with. We do a lot with startup companies, so we really enjoy this whole Y Prize process, and that something really interesting will come out of it in this cycle. So we have a lot of licensing professionals that work at PCI. I have a team of folks. I have counterparts that have teams that do things out of the School of Medicine and other areas of campus. My group focuses on School of Engineering, Arts and Sciences, Wharton School of Business, and the School of Design. We do things like licensing. We help folks do startups. We can help facilitate corporate-sponsored research projects. We try to be as accessible and readily available as we can, so feel free to reach out to me or anyone on my team. Terry has my contact information, and I'm also happy to provide a copy of the slides if anyone has an interest in that. And we do a lot of education accelerator programs, and we provide resources to help both faculty and students try to develop their technologies. So sort of more broadly in the community, how can we potentially help you? We work with a lot of strategic partners. There's Life Sciences Pennsylvania, which is a little more medically oriented. There's the PAC group, Philly Startup Leaders, Amplify, Tech Philly, Ben Franklin Technology Partners is a very prominent VC group in the area. Intellectual Property Group, a State University Partners, another prominent VC group in the area. There's also a Philly Nucleate chapter, which I think is maybe housed here in Wharton. I know I've interfaced with those folks in the past too, and encourage you to seek those out as well. We do a number of events. We do a celebration of innovation every year where we recognize our faculty inventors, and we give them a nice little cue recognizing patents that have been awarded. We do various national showcases, including J.P. Morgan and South by Southwest. And we have a speaker series where we have speakers both in the fall and spring semesters that come in and talk about various topics related to entrepreneurship, startup companies, things of that nature. So I encourage you to look for those. Those are generally held in one of the School of Engineering buildings, and we typically have 2 in the fall and 2 in the spring. We're also planning to do a startup workshop, hopefully later in this fall, which will have all the different stakeholders that you need to kind of pull together to stand up a company. So I hope some of you will find that interesting and feel free to attend that if you can. We also participate in a lot of programs. We participate with the President's Innovation Prize, the Y Prize, which is why we're here tonight. We have the Penn Center for Innovation Fellows. These are typically graduate students that are also work with us to help learn about entrepreneurship, but also how to analyze technologies and inventions that we get in the door, and how to translate these into commercial opportunities. We have the Innovation Center, which I talked about in the accelerator. We also house the NSF-funded I-Core program, which is a great way for you to sort of test out your idea, do some customer discovery, so I encourage you to look into that if that's something of interest to you. And then our PCI Ventures group has several different programs, including Upstart and Up Advisors, where they can help guide you through the startup process. This is a little bit more about the I-Core program. Again, you can find that online on our website. And just sort of what we call the help desk. These are different resources that we can point you to give you some guidance, both internally as well as externally, around Penn, FAQs, events that are potentially helpful, maybe of interest to you. We have an inventor portal if you have something to disclose. It's a very easy interface for you to enter the information, tell us what you think you've come up with as an invention. We have a helpline with a phone number and email, and then we can point you to certain external resources, such as companies that work in the innovation space, prototyping labs, things of that nature that may be more sophisticated than what is available within Penn, and agencies and other folks that might be able to help you. So that's it. I think I stayed within my 5 minutes. I'm happy to answer a question or two, and I'll stay afterwards here in the reception session. Folks have questions in. So, any immediate questions that come to mind? Okay. So you either understood everything or just completely confused.
Or they can always come to me if there's any questions. I can always point you to Terry. So thank you so much. Okay, we're just about done. I just want to spend a couple minutes because I think this is really important for you guys. We have our last year's winners here, or a couple of our team members. So I wanted to invite up a couple of the members from Team Lily Loop who won last year. You guys, you have slides? Do you have slides? Yeah. Okay. Why don't you come on up, and why don't you just give a couple minutes on your experience and what you thought about the Y Prize, and while you do that, I'm just going to put up a little bit about the timeline for this year. Woohoo!
So hi guys, my name is Kylie. I'm a sophomore right now studying computer science and finance at MIT.
I'm Neha. I'm a sophomore in LSM. I'm studying biology and healthcare management. And Rima is also on our team. She's also a sophomore in LSM. She couldn't be here today, but she's on our team.
Yeah. So we competed in Y Prize last year, and we won with our application Lily Loop. So essentially the technology last year that we used was a biodegradable soil moisture sensor from the Turner Lab. And our application was applying these sensors to essentially perform quantitative blood loss on like diagnosing irregular menstrual bleeding disorders earlier. So after we competed in Y Prize, we did a lot of other Penn competitions, and they have a lot of resources that the Mack Institute helps us with. So we were able to get in touch with PCI, and then we competed in I-Core. There's a nanotechnology entrepreneurship competition, Holt Prize, and then also the startup challenge, like I think Sebastian left, but like Sebastian mentioned earlier. And then we were also able to work on the startup this summer, and I was able to intern in the Turner Lab to understand the technology better.
Yeah, but we were a group of 3 freshmen coming in. We didn't have any experience in building a startup from the ground up. We just came to the info session. Me and Kylie actually met there, and now we're like really good friends. We're continuing to work on the project, and we've learned a lot about how a business operates, how to pitch effectively, how to communicate ideas, how to think about startup financing, how to think about market fit, product market fit, all these kind of things that you'll learn about, I think, if you participate in the Y Prize. So don't let any lack of experience or lack of knowledge stop you from entering. I think our biggest pieces of advice are to think about ideas that are creative and relate to you and your experiences and the experiences of your team personally. Build a team of people that come in with a diverse range of experiences. Don't be afraid to reach out to labs that are developing the technologies. They're really good resources for thinking about technology feasibility with your idea, which is something that I think the judges look for. And then I think team morale is a really good thing. So the 3 of us are really close, and we've learned a lot in the process. And I think that's what kept us going and why we're still working on the idea. But we've learned a lot in the process. Feel free to come to us with any questions. I'm sure Terry can share our information. But yeah.
Thanks, guys. Thanks, guys. I appreciate it. Okay, so that concludes our schedule for tonight. We want to get you over to the reception that's happening over in Joe's Cafe. So take the time, eat, drink. But before we do that, this is the schedule for the competition. All of this will be prompted via email in the next coming weeks. But the next event on the schedule will be next Tuesday, October 1st. We're having a tech briefing to take a deeper dive into the technology. So make sure you spend some time to learn about that. I also want to just draw your attention to one more thing. As you guys think about forming a team, it's best, when that happens organically in the person, that's great, but if that's not possible, we do have a Google Doc on our website, on our yprize.upenn.edu website. It's a live document if you're looking for a team. There's a spot here to put your name. You can indicate, your school, your major. If you're looking for a team, if you have a team and you're looking for members, there's contact information. It's a great opportunity, a great way to meet people. If you're looking for team members. Go ahead. There's no limit. I would say average in the years I've been doing this, it's somewhere between 3 and 5. I think the biggest thing to keep in mind is the most successful teams. I think in anything are the ones with diverse skill sets, as the girls mentioned. So I think it's best to don't be a team of all engineers, don't be a team of all business people, don't be a team of all arts and science people. Definitely mix it up. So, but there's no limit, there's no requirement they have to be a Penn student. The requirement is that at least one team member. The requirement is that for teams, at least one member of the team has to be a Penn enrolled student. Okay, so go ahead and head over to Joe's, and thank you for coming.
I don't care enough. Thank you very much.